Hello friends, let us now learn some important points about the process of X-ray generation. So if you see in the process of X-ray generation, what actually happens is that when a fast moving electrons from the cathode, when they bombard the target anode, then X-rays are produced. Okay, now you have to see E is the kinetic energy of electrons. And if you see small e is the charge of the electrons, P is the voltage passing across the cathode and anode, then we can say that E is equal to, that is kinetic energy of the electrons is equal to a charge into voltage. So this is the electron volt. Electron volt is the energy of the single electron obtains when crossing 1 volt of potential difference. So this energy equal to charge of the electron is 1.6 into 10 to the power of minus 19 coulombs into 1 volt, that is equal to 1.6 into 10 to the power of minus 19 coulomb into volt, we get joule. So now we have something called as kilovoltage peak. Kilovoltage peak is the potential difference which is applied between cathode and anode. This is called as kilovoltage peak. Then we have something called as kilo electron volt. So what is this kilo electron volt? Kilo electron volt is actually the kinetic energy which is applied, kinetic energy or voltage of the applied voltage which pulsates between the some lower value and the maximum value of kVp selected. So this is the kinetic energy. Kilo electron volts is the kinetic energy of this electron, which is which will which the electron has when it is bombarding the anode. Then what actually happens? There are two different types of generation of X-rays. We have number one, general radiation, which is also general radiation, which is also called as Bremsstrahlung radiation. Second, we have photoelectric effect. Okay. So what happens? First, we will learn about the production of general radiation or Bremsstrahlung radiation. In general radiation or Bremsstrahlung radiation, when an electron comes and this is the nucleus, and this is the K shell, and this is the L shell. The more shells are M, N, O shell. The K shell is attracted to the nucleus. So the energy of the K shell, that is K shell binding energy, the energy by which the electron in the K shell is bounded to the nucleus is called as K shell binding energy. So this K shell binding energy is more than the L shell so energy of the K shell is more than binding energy of L shell, more than binding energy of M shell, more than binding energy of N shell. Because the electron is bound to the nucleus, so this binding energy is in negatives. Okay. Now, what is important here is that the when the electron comes and comes near the atom or near the nucleus, these high speed electrons are in a way attracted to the nucleus. Okay, the electron has negative charge and the nucleus has positive charge. So the electron is deflected towards the nucleus and it is attracted towards the nucleus and it is deflected from its original direction. While the electron is attracted towards the nucleus and deflected from its original nucleus, the electron will slow down and lose certain amount of energy. The amount of energy that it loses is emitted as X-ray photon. So we have the kinetic energy of electrons. This kinetic energy of electron is lost directly here in the form of photon. Okay, the remaining kinetic energy of this, the electron will have some kinetic energy. So it will strike one more, it will go near um, one more atom, and then it will interact with one more atom, and it will produce even more radiation, X-ray radiation. So when most electrons strike the target and give up their energy after multiple interactions with a number of atoms, when they interact with a number of atoms like this again and again, then they lose most of their energy. So here electron is giving up their energy, so as a result the electron is stopped at the end, so break is seen. So this is called as Bremsstrahlung radiation. Bremsstrahlung in German means breaking radiation. Sometimes the electron may directly collide with the nucleus and it will release all of its energy as a single X-ray photon also. Usually, generally, if you see, the electron will undergo many reactions with multiple atoms before it comes back to rest. So each time the electron comes near the nucleus of each atom, it will release a small amount of energy as X-ray photons. There are two factors which will cause distribution of this energy which is produced by the breaking radiation. Okay, this kinetic energy of electron, among this 99% of this kinetic energy is lost as heat, whereas only 1% of it is converted into X-ray. So what are the two factors which will cause the distribution of energy before it comes back to rest? Number one, the electron coming near the nucleus. This is one factor. The other factor is electron going directly or having head-on collision with the nucleus. With both of these, the electron is stopped, and thus the radiation or X-ray is produced. So X-ray is actually a photon. Okay, because it is a photon or a type of radiation, it will have the wavelength. The minimum wavelength of this X-ray photon can be calculated with the formula 12.4 by kVp. So if you take an example, if we are using a 100 kilovolt peak of X-ray tube, this 100 kilovolt peak of X-ray tube will require 100 kilo electron volts. So minimum wavelength of X-ray photons which are produced are 12.4 by 100, that is almost equal to 0.124 angstroms of wavelength of X-rays are produced. See, when the electron is reflected, a small amount of its energy is converted into X-ray, or when the electron has head-on collision, complete kinetic energy of electron is converted into X-ray photon. Meaning that for the X-ray photon, there will be these X-ray photons will have small amount of energy photons are released. At the same time, high energy photons are also released. So there is a range for the X-rays, range of energy of X-rays are released when the electron undergoes Bremsstrahlung radiation rather than one single um, amount of energy. So as a result, this wavelength is actually the minimum wavelength of minimum wavelength that an X-ray photon can have while using this 100 kilovoltage peak of X-ray tube. So by this we can tell that the different energies or a range of energies of electrons reach the target. When range of energy of electrons reach the target, they will emit range of energies of X-rays which will contain a range of wavelength of X-rays. Okay. Now, if I have to draw a graph from Bremsstrahlung radiation, if I have to draw intensity over wavelength, this is the minimum wavelength, which is lambda minimum. Most of the wavelengths will be in the just immediately, and then slowly they will decrease. So this is how the spectrum of Bremsstrahlung radiation is seen. The next important thing is photoelectric effect, also called as characteristic radiation or photoelectric effect. So what is this characteristic radiation or photoelectric effect? So here what actually happens is that there is electron will come and it will have head-on collision, or it will directly collide the inertial electron. This inertial electron is actually the K shell electron. This K shell electron is bound by the nucleus by an energy called as K shell binding energy. When this electron has energy, the kinetic energy of electron is more than the K shell binding energy of this electron, then it will directly hit the electron, and this electron is ejected from its inner orbits. This removal of electron, once the electron is ejected, and this initial electron will also change its direction, change its path, and it will also come out of it, and it also goes out. And this electron will hit one more nucleus and it produce one more energy radiation. So what happens is this: whenever the electron is hit, then there is a hole which is created here. This hole or this positive charge is created in the inner shell. So an outer shell electron will come and it will try to occupy the inner shell electron. So when an outer shell electron will try to occupy inner shell electron, then it is emitted as X-rays, or radiation is emitted as X-rays. So the ejection of this uh, this X-rays are produced. So binding energy of electron in a K shell is around 70 kilo electron volt. So this cathode electron, we should have a kinetic energy of more than 70 kilo electron volt in order to eject the electron from its inertial orbit. If it has energy of only 60 kilo electron volt, it cannot eject the electron from its inertial K shell orbit, and thus photoelectric effect cannot happen. So once it ejects the electron, so this K shell, whenever there is no electron in the K shell, obviously it becomes unstable, and as a result, L shell or M shell, electron from K shell, from electron from L shell or M shell will start and will come down, will descend, and it will occupy the lower shell electron. Because the excess energy, when electron jumps from K shell to L shell, this excess energy is liberated as X-rays, are ejected as X-rays. Now, if you see, the K shell has binding energy of 70 kilo electron volts, L shell has binding energy of 11 kilo electron volts. So the difference of around 59 kilo electron volts, this is converted into X-rays. Okay. So based on the shell which it moves, like from K shell to either it is L shell to K shell, based on the shell from which the electron jumps or moves into the K shell, we have different types of characteristic radiation. If energy from L shell moves to the K shell, a vacancy is created in the L shell and K shell is occupied. Now again, an electron from the M shell, that is outermost electron, will come and it will occupy this vacancy in the L shell, and during that time again X-rays are produced. So this radiation, where an electron from M shell will come down and occupy the L shell, is called as L characteristic radiation. So based on this, in one atom there are many types of characteristic radiations seen, and different energies are ejected. So for this we can draw a graph. So this is the Bremsstrahlung radiation, which is a continuous spectrum of radiation, but we have characteristic radiation where specks of energy is released. So we have alpha 1 and alpha 2. So what are these alpha 1, alpha 2, beta 1, beta 2? Alpha 1 and alpha 2, this alpha 1 and alpha 2 are seen when an electron from L shell moves to the K shell, then alpha 1 and alpha 2 are produced. We have beta 1. In beta 1, when an electron from M shell goes to K shell, then beta 1 is produced, and an electron from N shell goes to K shell, then beta 2 is produced. So Bremsstrahlung radiation is a continuous radiation, whereas characteristic radiation, many specks of energy is produced. So for example, think that there is, so according to this graph, we can tell that below 70 kilo electron volts, see, the 70 kilo electron volts is the binding energy of K shell. So below 70 kilo electron volts, there is no characteristic radiation. There is no characteristic radiation seen between 70 kilo, below 70 kilo electron volts. Between 70 and 150 kilo electron volts, between 70 and 150 kilo electron volts, characteristic radiation or K shell characteristic radiation is seen. And above 150 kilo electron volts, here there is no characteristic radiation is seen. And if it's more than 300 kilo electron volts, there is negligible characteristic radiation is seen. So this is about the different types of Bremsstrahlung and photoelectric effect. Then next important thing is about the intensity of the X-ray beam. Okay, we have to see the intensity of X-ray beam. Intensity of X-ray beam can be defined as the number of photons in the beam. If you multiply number of photons and into beam multiplied by energy, we get the intensity of X-ray beam. Number of photons multiplied by energy of photons will give the intensity of X-ray beam. So the units of intensity of X-ray beam is Roentgen per minute or coulombs per kg in SI unit. So there are factors which will affect the intensity of X-ray beam. The factors which affect the intensity of X-ray beam are kilovoltage peak, X-ray tube current, target material, that is the anode, and also the filtration. Filtration we will learn in our later classes, but in this class we will learn about these three. So first let us learn some important points about the target material. So if you see, this is the target material, that is tungsten target material. Target material used will determine how much energy or how much radiation is produced at a given applied voltage. So the target material, normally we use tungsten as the target material because of its greater efficiency, because it has 74 atomic number, higher atomic number, so it can produce uh, greater efficiency of X-rays are produced when compared to other metals. Number two, the tungsten also has good melting point of 3370 degrees Celsius. So because of its high melting point, it can dissipate the heat better. So for continuous spectrum, that is Bremsstrahlung radiation, the atomic number of target material determines the quantity of X-rays produced. If you see the tungsten, we are dealing with tungsten. Tungsten has K shell binding energy of around, so if you see for tungsten, the K shell characteristic X-rays will range from 57 to 69 kilo electron volts, whereas for tin, the characteristic K cell characteristic X-rays will be around 25 to 29 kilo electron volts. For lead with atomic number of 81, tin has 59, has a 50 has atomic number, tungsten has 74 atomic number. So for lead, the characteristic X-rays will be between 72 to 88 kilo electron volts. So if you see, has the atomic number increases, the characteristic X-rays increased. The energy of the characteristic X-rays increased, and we require characteristic X-rays of optimum duration, optimum levels. So tungsten is used as a good target material. One more target material which has been used is molybdenum. Molybdenum, see, with higher atomic number like tungsten, X-ray beam mainly contains Bremsstrahlung radiation. Molybdenum has low atomic number when compared to tungsten. Because of the low atomic number of molybdenum, if we use this low atomic number molybdenum with lower tube currents, so this will produce here with this molybdenum with lower tube current, this will decrease the Bremsstrahlung radiation. The Bremsstrahlung or characteristic radiations are decreased and there is increase in photoelectric effect is seen. And this this Bremsstrahlung radiation is decreased. So because the Bremsstrahlung radiation is decreased, the photoelectric effect or characteristic radiation will increase. So because the Bremsstrahlung radiation is decreased and photoelectric effect will increase. So for mammography, in mammography tubes, we use molybdenum at around 40 kilo electron volts, and this will produce 17.5 kilo electron volts of K alpha characteristic radiation, and it will also produce 19.6 kilo electron volts of K beta characteristic radiation. So as a result of this characteristic radiation, we can use this molybdenum in mammography. Then we should learn the factors which are there. This is about the target. We have learned about the target material. The next we have to learn the factors affecting the intensity of X-ray beam in that kVp and tube current. So we have, if you see the kilo voltage peak applied, if you draw intensity with wavelength for different kilo voltage peak or voltage, as the voltage increases, the intensity increases, but the wavelength remains same. So we can say that intensity is directly proportional to the kilo voltage peak whole square. The wavelength of the characteristic radiation is constant, but as the energy of the electrons is determined by the kilo electron volt peak, so increased kilo voltage peak will cause increased X-ray production, increased intensity of X-ray production. Then, similarly, tube current also. As the number of electrons striking the target increases, the tube current will increase. If there is higher tube current, increased tube current will result in increased intensity of X-rays. But the wavelength of X-rays will remain constant even at lower or higher tube currents. So these are the important factors which are influencing the X-ray production and X-ray intensity. Thank you.